In this video, we're going to derive some more trig identities, namely the angle sum and angle difference identities when we're using sine, cosine, and tangent. Just a reminder that an identity holds true for all values. So let's consider the unit circle that we've got shown here, and we've got points P and Q lying on the unit circle as shown in the diagram. So what we're going to do first of all is we're going to have a look at the angle making P, and we're going to call that angle A. And we're going to have a look at the angle formed to form point Q, and we're going to call that angle B. So what we want to try and do is try and define the distance from PQ. Now, using our understanding of the distance between 2 points being a straight line, we want to say point P, its coordinates take point Q, and we can use Pythagoras to do this. So if we consider, we're going to have a look at the difference between the y values between those 2 points and the x values. Now we can remember from our work that if we want to find point P, it's got in terms of trig ratios, it's just the x values represented by the cos of angle A and the y values of the sine of angle A. And for point Q, it has the coordinate cos of angle B and sine of angle B. So using this information, using the distance formula, we could say the distance is equal to the square root of the difference between the x values. So we can say cos A take cos B squared plus the difference in the y values, sine A take sine B squared. And then we're going to have to use some algebra to derive these. So I'm going to just use that in this first one here. We're going to expand this. So we've got cos squared A take 2 cos A times cos B plus cos squared B, and we would have sine squared A take 2 sine A sine B plus sine squared of B. Okay, let's see if we can simplify this down a little bit. What I have identified is we've got cos squared A plus sine squared A. We know from our Pythagorean identity that cos squared A plus sine squared A equals 1. So far we've got these equaling a 1. And also we've got cos squared B plus sine squared B, which will also give us a value of 1. So that's taken away a few terms. And then we've got take 2 cos A times cos B, take 2 sine A times the sine of B, all under that square root. So the distance, really, if we just clean this up a little bit, is 2 take 2 cos A cos B, take 2 sine A sine B. Not much more we can do with that at the moment. But let's consider if we use the cosine rule to find the distance of PQ. So if we think back to what PQ looked like, and if we look at the triangle that's formed from the origin out to P and out to Q, and then the line drawing them, let's just redraw that below. We're dealing with this situation here. We have P, we have Q. They are both made up of the radius of 1, and we have this angle in here. And that angle is angle A take angle B. So if we used the cosine rule to define this, we would have the square root of 1 squared plus 1 squared take 2 times 1 times 1 times the cos of the angle, which is A take B. So essentially what we've done is we've just identified 2 different ways of expressing the distance between point P and point Q. Essentially these should be the same value. So in making that comparison, we're essentially saying that both of these are equal. What I am going to do is just simplify our second one for us. 1 squared plus 1 squared is 2. 2 times 1 is 2. Cos A take B. That's going to make it easier. So let's bring those two down here. So we've got the square root of 2 take 2 cos A take B should be equivalent to the square root of 2 take 2 cos A cos B take 2 sin A sin B. Let's neaten this up because we don't need all these square roots. So let's square each side to get rid of the square root sign. So let's get rid of that and get rid of that square root. Okay, that looks a lot better. And I can see that there's a factor of 2 running through here. So if we can take out a common factor of 2 from each side, we can divide both sides by 2, makes them disappear. So what we're left with is 1 take cos A take B equals 1 take cos A cos B take sin A sin B. So I'm going to write that down so we can see that a little clearer. And now I'm thinking if I get rid of this 1 here by taking 1 from each side, those ones are going to disappear. And I don't like the fact that they all have a negative out the front. So, whoops, I'm going to essentially multiply through by -1 or rearrange them on each side. And I end up with cos A take B equals cos A times cos B plus sin A times the sine of B. And what I've just done is created an identity about the difference between two angles, A and B. So the cosine of the difference between two angles will always be equal to the cos of A times the cos of B plus the sine of A times the sine of B. So now we've got a second identity. We've got the Pythagorean identity and then this identity. So let's actually consider what would happen if we replaced the B with a negative angle B. So what we know from this is that if we consider, for example, the cos of B, so if we had an angle B, if we change this to the cos of negative B, it means that we're just going to have this angle down here. We think about that ends up in the fourth quadrant. Cos is positive in this quadrant. So cos of negative B is just the same as cos of B. But if we change sine from a B to a negative B, down in this fourth quadrant, sine is negative in this quadrant, so that would just be the negative sine of the acute angle B. So let's have a look at what happens if we had an angle sum instead. We wanted to say the cos of angle A plus B. So let's use our previous identity that we've just formed, but let's change it to cos of A take and replace the B with a negative B, which is going to make that become a plus essentially. So what's that going to do is we're going to have cos A times the cos of negative B, which we know is just still cos of B, and plus the sine of A times the sine of negative B, which we know is the negative sine of B. So what that is essentially going to do is turn this plus into a minus. So if we have the angle sum in a cosine situation of adding angle A and B, we will have cos A times cos B subtract sine A times sine B. So we can clearly see that there's a bit of a pattern going on here. Now we want to have a look at using sine, and we're doing sum of angles and the difference of two angles. So we need to look back and remember something about the things that we know in terms of cos 90 take an angle equaling the sine of an angle. So if you think back to some of our values, our exact values, for example, if I said to you sine 30, and that's equaling to a half, that should be equal to cos of 90 take angle A 30, which is in fact cos 60. Yes, cos 60 is a half. So let's make sure we can establish that using the right angle that we have here. So sine A should be opposite over hypotenuse. So we're looking from this angle. But then if we look from the other angle, and we look at cos of 90 take whatever A is, because it's a right triangle, that's also the adjacent over the hypotenuse, which is also A over C. So yes, we totally agree with this in terms of not knowing some values plus working it out in a general form. Let's have a look at the sine of 90 take the angle. So if we look from the angle 90 take A, we do opposite over adjacent will be B over C, which we can see in our triangle. And the cos looking from angle A is the adjacent over the hypotenuse, which is also B over C. So we can see that yes, that definitely holds true. So let's use this to actually establish the difference between two angles using sine. So if we take this as sine of an angle, like angle A, they're telling us that that's equivalent to cos of 90 take the angle. So here we have A take B. So this is equal to cos of 90 take that angle A take B. So let's just get rid of that bracket. We'd have 90 take A plus B. Now if we regroup that 90 take A and use our rule here about cos of an angle A plus any angle B, which we had from earlier, which was the cos of A, which we've got, the first angle is 90 take A times the cos of B, take the sine of the first angle times the sine of B, the second angle. And we know that 90 cos of 90 take A is the same as sine A. So we can write that as sine A times the cos of B and take. And we know sine 90 take A is the same as cos A. So it's cos A times the sine of B. And what we've just done is created an identity for the angle difference between angles A and B when using sine. That's sine A times the cos of B, take cos of A times the sine of B, which we've established here. So what we can do is work out what happens if we replace B with negative B so that it becomes sine A plus B. How does that change the identity? Well, much in the same way as before, remembering that if we replace sine B with negative B. That angle B, becoming negative B, falls in the fourth quadrant. Sine is negative, whereas cos of negative B, cos is still positive in that fourth quadrant. So if we could reconsider this, we would have sine of A take negative B would be the sine of A times the cos of negative B take the cos of A times the sine of negative B. But we know that cos negative B is just cos of B, and we know that sine negative B is the times the negative sine of B, so that's going to change this sign to a positive. And so we see that when we're doing the angle sum using sine, it becomes an addition. And we've created an angle sum identity for sine. Now this might seem like a lot of information about how these identities have come about. You don't have to worry about knowing how these and being able to show how these identities have come about, but it just gives you a background that's not just some arbitrary thing that we're telling you. They're formed out of all of our knowledge to do with right triangles and the unit circle and how the sine of an angle and the cosine of an angle relate to each other. If you would like a bit of a challenge, have a go at deriving the identities for the tan of angle A plus angle B or tan of angle A take angle B, using the fact that we know the tan of an angle is the sine of the angle over the cosine. So basically you're going to expand on the fact that sine A plus B is sine A times the sine of cos of B plus the cos of A times the sine of B over the cos of A times the cos of B take the sine of A times the sine of B. And then you can start simplifying from there and see if you can actually come down to prove these identities that we have here for tan. But more importantly, it's the fact that we need to be able to use these. So let's have a look at a couple of quick examples. So if you saw sine 6x times the cos of x plus cos 6x plus times the sine of x, what is that actually representing? Well, we can clearly see that we've got the sine angle sum happening here. So really this is just the same as sine of 6x plus x, because it's got the plus here, and we've got the sine times the cos and cos times sine. So we can simplify this as it representing the sine of 7x. If we had to simplify the next one, which is cos 4x times cos x plus sine 4x times sine x, this is one of the cosine identities, and it's the angle difference. It's 4x take x, which we can simplify to cos of 3x. So not only can we use the identity to expand, we can use it to simplify. But here's the reason why we can use these identities. If we have a look at question 3, it says determine the exact value of sine 75. Now in our minds, 75 is not a beautiful exact value that we know, not like sine 30 is a half, or sine 60 is root 3 on 2, or sine 45 is root 2 on 2. But what we can do is use that identity to break down 75 into ones that we know. I know sine 75 is 45 plus 30, which means I can use the angle sum identity for sine, which is the sine of 45 times the cos of 30 plus the cos of 45 times the sine of 30. Well, this tells me that I can simplify this because I've got now my trig exact values. Sine 45 is root 2 on 2 times cos 30 is root 3 on 2, and cos 45 is root 2 on 2 times sine 30 is a half. So I can simplify these. This is root 2 times root 3 over 4 plus root 2 over 4, which I can put these together. I've got a common denominator, and I can even see they've got a common value. So I could say it's root 2 outside of root 3 plus 1 over 4. So this is where we use these identities to be able to express angles exactly in terms of sine, cos and tan when they're not true exact values that we know. So my goal for you is to have a bit of a look at where they come from, but ideally identify them, know them, how to use them to express values exactly. So what I'd love you to do is have a go at number 4 and see where you can go from there.